Alright, so I'm going to work out example 1 here. Again, I'm going to assume that you've read this problem, that you've tried to work this problem. I'm not going to read through the problem statement all too much, although this is pretty short. Basically, it describes a spherical conductor that has some charge on it. There's another charge that's near that spherical conductor, and we're trying to calculate what the net electric field is at some point. So the first thing that I'm going to do is just get a picture drawn that illustrates where the charge, the sphere, and the place that I'm trying to calculate the field are all at with respect to each other. So I've got a spherical conductor here. I'm told that that's at the origin. So let me just sort of draw an x-axis and a y-axis. I've got another charge that is sitting at the point plus 4 centimeters, minus 4 centimeters. So that would be somewhere down around here, and then I'm looking for the field at a point negative 4 centimeters, negative 4 centimeters. So that would be somewhere over here. Now the radius of the sphere is given, and that is 2 centimeters. And I'm told that there's a negative 2 nanocoulomb charge on that sphere, but I'm just going to call that capital Q. All right, so it could be positive or negative. When we get down to the final answer and I need to actually calculate a number, I would just plug in the negative 2 nanocoulombs for that. So in this case, Q is negative 2 nanocoulombs. And then I've also got this charge down here in the bottom right quadrant, and I'm going to call that Q, just lowercase q, and that's going to be the plus 2 nanocoulombs. Now I've also got coordinates here, so I know that the sphere is at the origin, so that's 0, 0. I'm just going to call the coordinate of the second charge, I'm going to call that x1, y1. So in this case, x1 is going to be equal to the 4 centimeters, and y1 is going to be equal to the negative 4 centimeters. And I'm going to do the same thing for the point that I'm looking at the electric field at, and I'm going to call that x2, y2. So x2 would be equal to the negative 4 centimeters, and y2 would be equal to the negative 4 centimeters. And I'm just going to do this so that I don't have to, keep these numbers. If I'm plugging in numbers immediately, then I have to keep track of all of these units, and doing the algebra with a bunch of units in place just kind of can be a pain. So I'm just going to write down, x1, y1, x2, y2 for now. All right, so let's see here. The first thing that I need to do in this problem is figure out what is the electric field due to this sphere going to look like, right? So I've got a sphere here. It's going to produce some electric field. How do I know what the electric field due to that sphere looks like? Well, for that we just need to consider what the properties of conductors are, because we're told that this is a conducting sphere. So we know that any charge on a conductor is going to uniformly distribute over the surface of that conductor. So we know that the charge is going to be uniformly distributed over the surface of a sphere. And if we have a spherically symmetric charge distribution, then the electric field due to that charge distribution is going to look just like a point charge when we're outside of the conductor. So basically what I'm saying is that this conducting sphere can be treated as a point charge at the origin with a charge Q. And the electric field outside that sphere is going to look the same as it would if it was really a point charge there. Now, of course, inside the sphere, the electric field is going to be 0. So inside the radius of the sphere, the electric field does not look like that of a point charge at the origin. But it does look like that of a point charge at the origin outside. So I know that this is going to be, I'm going to be able to replace this with a point charge. So I'll just draw the point charge there. All right, let's assume that both Q, well, actually I've got here, let me see. I've got a negative Q and I've got a positive little q. So I'm gonna assume that yes, big Q is negative, little q is positive, and I want to draw what the electric field due to each of those charges should look like at this observation point, and then sketch out what the net field should look like. So let's say my observation point is here. The field due to this little q charge is going to point away from the positive charge, so it should look like this. And then the field due to the charged sphere, since it's negative, the electric field is going to point towards it, and it should look like this. Which means that the net should point somewhere like this, and it's that net field that I'm trying to find. So the way that I'll go about doing this is first find the field of the little q and the big Q charges as vectors, and then add those vectors together. So I need to figure out what is this arrow and what is this arrow, right? Those are the vectors that are the field for each. The field here, so that field's actually going to be fairly straightforward because I already know that it points in the negative x direction, but this field does not point in the x or y direction. It points in both, and so what I do need to do is figure out what some angle is. I'll try to figure out what this angle is. That's the angle with respect to the positive x-axis. So I'm going to try to figure out what those two vectors are first, and then I'm going to add those two vectors together. Alright, let's see here. Let's do the simple one first. Let's look at the field due to the little charge q. So I know that the magnitude of that force is given by Coulomb's law. Oh, excuse me, hold on. I'm not doing force, I'm doing field. So let's see here. The magnitude of that field, it was almost like Coulomb's law, is going to be kq over r squared. Now this r squared is the distance between the charge that I'm looking at and the place that I'm actually observing the field. So r, in this case, is going to be this distance here, right? That's the distance between the point that I'm observing the field and the charge that's creating the field. And so that distance is just going to be the x position of the charge minus the x position of my observation point. Right, so in the example that I have, this is going to be 4 centimeters minus negative 4 centimeters, which will give me 8 centimeters. And I need that squared, so r squared is going to be x1 minus x2 quantity squared. I'm given what the charge is, so the electric field strength is just going to be kq over x1 minus x2 quantity squared. Now that electric field is a vector, so there's a direction associated with that, and I can just tack that on now. I know that it's going to be at 180 degrees with respect to plus x. So this is plus x, 180 degrees to the direction that the field actually points. Alright, so I've got that one done. Now I'm going to work on the field due to the charged sphere, so I'm going to look at this guy. Figuring out the magnitude, well, actually I need to know how far away I am from the origin to figure out the magnitude. So what I'm going to do is I'm going to draw a triangle that's going to help us solve this problem. So let me draw the origin here, draw the position that I'm trying to find the field at, draw a line that connects those two, and then draw a horizontal line here, right? So this would be a 90-degree angle. Well, if I draw that triangle separately, I would find that the length of the horizontal side here is just going to be x2, and the length of the vertical side, let me put absolute value around that, and the length of the vertical side is going to be y2. And then there's going to be some angle here, which is actually the angle that I'm looking for, because the electric field is going to point along that line like this. So how far am I from the origin? Well, I just need to calculate the length of the hypotenuse on this triangle. So the distance for this case, right, so this would be the distance that goes into Coulomb's law, or sorry, I keep saying Coulomb's law. I'm talking about the distance that goes into the electric field calculation, right? It's 1 over r squared. So that distance would be x2 squared plus y2 squared square root of. This is just Pythagorean theorem. So r squared must be x2 squared plus y2 squared. Alright, so I can calculate what the magnitude of that field is then. So the magnitude of the field due to the sphere is going to be k. I've got a Q here. I'm going to keep the negative sign in that symbol, right? So just remember that this capital Q actually is -2 nanocoulombs, and I'm going to divide by the distance to that charge, to the origin, squared. So I've got x2 squared plus y2 squared. So that will give me the magnitude. Now I need to figure out what this direction is, and I can use the same triangle to figure out this direction. Now this is a pretty simple case. The length of the, if I look at this triangle here, let me get my pointer out. So if I look at this triangle, I've got an angle here, right? And if I'm going to apply trigonometry, then this angle determines what the opposite and adjacent sides are. Now this long side is always called the hypotenuse, but with respect to this angle that I have drawn, this bottom side is the adjacent side, and this vertical side is the opposite side. Okay? So I could use trig to figure out what that angle is in terms of the length of the opposite side and the length of the adjacent side. And that's what I'm going to do. Now, because those two sides are of equal length, I know that this angle is going to be 45 degrees. But let's just assume that we want to calculate this in general in case x2 and y2 change for some reason. All right, so the way that I would go about calculating that angle is I would write down that tangent of that angle is equal to the ratio of the opposite side over the adjacent side. I need to put absolute values around there in case one of these coordinates is negative. In this case, x2 is a negative number, and the ratio here needs to be positive if I'm going to get that angle right there. So that means that the angle itself is the inverse tangent of that ratio. So y2 over x2, absolute values. And I could calculate that. Now, what I'm going to get, if I do it with the numbers that I have, is I'm going to get the inverse tangent of 4 over 4, which is going to give me the inverse tangent of 1, which is going to give me 45 degrees. So that angle is 45 degrees. Now, that angle is with respect to the positive x-axis, because the positive x-axis points to the right. So this is plus x. So that means that I can say that the direction of that vector is 45 degrees with respect to plus x. Alright, so now I've got, let's go back up here a little bit. I now have the magnitude and direction of both vectors involved. Right, so this is the magnitude of the force, or excuse me, this is the magnitude of the field that's created by the little positive point charge. This is the magnitude of the field that's created by the charge on the conducting sphere. And then I've got the direction for both of these. So now I just need to add these together as vectors. And I tell you what, I'm already at 13 minutes, so I think I'm going to put that in another video. Alright, so there will be another video that picks up right where I left off here.